Okay, let's get started. So, yay, projector's working. So, any questions since last time? Yeah, so you don't have to do it now, but whenever, if you have something that you haven't picked up, please pick it up. They are a fire hazard at my house. All right. So, what were we talking about last time? Grammars, right? And specifically, what type of grammar did we talk about?
Regular.
Yeah, regular grammars. So, what's a grammar, just in general? Not necessarily a regular grammar, but just a grammar in general. Yeah.
It's I don't know.
What are the main pieces?
It has the variables,
Mhm.
terminals, start variable, and then the rules.
Yeah, that's it. So a grammar always has four pieces. So variables, terminals, rules, which we call R, and start variable, which we call S. Yeah.
So in class last time, when you were writing out what's in a regular grammar, you said like sigma is, and then you like dash, and said of terminals. So is it?
Yeah.
Is it just a set of terminals?
It's a finite set. I didn't want to rewrite a finite set.
Oh, okay.
Yeah. Any type of micro optimization of our time is good. Yeah. But now we're spending time talking, so yeah, whatever. Okay, so what made a grammar a regular grammar? So what particular properties does a regular grammar have? Or restrictions, or however you want to think of it. Something about the rules, I think. Someone refresh my memory? Yeah.
There was like, let's see, 5 main connection you can do with a grammar.
I think 5's a little big.
So there are 4 rules.
Oh, okay, yeah, 4 sounds right. So what are the 4 types of rules that we could have?
Variable to epsilon.
Okay, so variable goes to epsilon. What else could we have?
Variable to terminal.
Variable to terminal. What else can we have?
Variable to a variable.
Variable to another one, maybe the same one, and what else?
And then a variable to terminal and a variable.
Terminal and a variable. Okay, so these are the only rule types allowed. Let me turn that off. Okay, so these are the only rule types that are allowed. So you don't have to answer it now, but a great test question is, what if I just take the top 3 types of rules and not all 4? What if I take the first, the second, and the fourth one? What if I take the first, the third, and the fourth one, or the second, third, and fourth? So if I take a subset of the types of rules that we are allowed to have, do I get anything different other than the regular languages? Because what did we show last time about regular grammars? Can anyone remember what we did? Yeah. Yeah, so we took a regular grammar and we converted it into an NFA. And the idea was we make a state for each of the variables, and we just related the states together just like the rules are. And for the rules here that either go to epsilon or go to A, what did we do? So for the last two rules, they go from a variable to a variable, and we just related that with just a normal transition between the states. But the first two don't have a state at all on the right side. So what did we do? Yeah, we made a new final state and went to that final state. Okay, great. So every regular grammar, you can make an NFA for it. What about the other way? We actually showed a lot of that last time. So what did we do with that idea?
We were trying to make an NFA in the reg grammar.
Yeah. So,
And
no, the other way. So we're trying to make a regular grammar from an NFA.
Oh.
Yeah, so what did we do?
We first defined the variables and terminals, right?
Right, the variables are what in the NFA? Are states. So it's basically this idea, but just the other way around. Here, when we converted a regular grammar to an NFA, we made a state for each of the variables. Now, in the conversion from an NFA to a regular grammar, what we do is we make a variable for each of the states. So it's doing basically the opposite operation. So then what we do, let's just say we have this small example. Then we make a variable for each of these two states. And for each of the transitions, we make a rule for it. So Q0 goes to Q1 on input 1. So I'm going to make a rule, which is Q0 goes to 1 Q1. And then the other transition is Q1 goes to 0 Q0. So it's doing the exact same operation, but in reverse. Here we had originally we had a rule and we just made a transition out of it. Here we're taking the transitions and making rules out of it. It's doing the exact opposite order. But if you look at this grammar right here, just those two rules, can I make any string of terminals from those? Of just terminals? No, why?
There's no like end state.
Well, yeah. Well, look at the rules. So each one of the two has a variable on the right side. So no matter which rule I apply, I always will still have a variable with me. So if I want a string full of terminals, I got to get rid of that variable somehow. So what could we do?
Well, for the final states, what we did last time is we had the variable Q1 going to epsilon.
Ah, so for each of the final states, we can just say, we're done generating the string. And that corresponds to exactly when we're in a final state. Which means if we had that string to start with, we would have accepted it. So in fact, that corresponds exactly to what we need for the regular grammar. So we can convert any NFA into a regular grammar just by making a variable for each of the states. And for each transition, we make the origin state goes to the transition label, then the destination state. And for each of the final states, we have them go to empty. And that corresponds exactly to the computation that the NFA would have done. Because you could just follow through the computation. Well, that just results in applying the rules in that particular order. And if you land in a final state, you have the variable go to empty. And so you generated a string of terminals. Yeah?
Last time we had a state that had a self-loop.
Mm-hmm. Yeah, so... Yeah. It works exactly the same way. So if I have, like, say this, Q0 loops itself on 2, the destination state is the same state. So it would be Q0 goes to 2Q0. So it's just the same recipe, but it's just the start and the end state of that transition is the same. But it's the same idea. Other questions? Cool. So this actually shows that regular grammars are yet another formulation of the regular languages. So we have DFAs, we have NFAs, we have regular expressions, and we have regular grammars. You want another one? Probably not. So, but any questions on this? Thankfully, we won't have any more, I promise. Because now we're actually going to move on to the next big topic after regular languages. Finally. Okay, so let's look at this. So I'm going to make a grammar. It's not going to be a regular grammar, as we'll see. But I want you to tell me what the language of strings that it generates is. So let's look at this grammar. So there's only one variable, s, and there are only 2 rules in the entire grammar. Really small grammar. So I may have not mentioned this, and I probably should. This vertical bar means or, which means multiple rules. It's just a shorthand to say we have 2 rules right here. S goes to 0s1, and we have another rule, S goes to empty. We're going to be using this vertical bar over and over because I don't want to have to write a gazillion rules with the same variable. We just string them all together like this. It's just a nice shorthand. Okay, so we got this grammar. It's pretty close to a regular grammar. The only difference is that we have 2 terminals on the right side on either side of the variable. So what is the languages of this grammar, whatever it is? Well, let's see. Is the empty string in this guy's grammar? Can I make the empty string from the start variable? Yeah.
Wait, is it that entire side or
Yeah.
epsilon?
So this is one rule's right hand side, and another rule's right hand side is just the empty string.
Oh, that was one or. Okay, then yes.
Yeah. So I can apply S goes. I should have explained that better. S goes to empty. So empty's in there. So what's another string that's in there? Well, if we want to figure it out, we better apply the first rule, right? We better apply 0s1. So if we apply 0s1, then what strings can we get out of that?
0, 1.
0, 1. If we apply it twice, what can we get?
0, 0, 1.
0, 0, 1, 1. See a pattern?
Yeah, it's 0 and 1.
Ah, so the language of this grammar is 0 to the n, 1 to the n, and at least 0. So, and what do we know about this language?
It's not regular.
It's not regular. Ah, so this 2-rule grammar, whatever it is, has more power than any regular grammar. Because this language is not regular, there is no regular grammar for it, by definition. But I found a 2-rule, very simple grammar for it. So what we're going to do is expand on this idea by not restricting you in any way what can appear on the right-hand side of a rule. So if we look at this, well, what were we doing before? We were looking at we were looking at what we were deriving so far, what we've made so far, picked a variable, and then applied a rule to it. Well, before, we always had one variable to start with, and we always will have one variable until the very end. So we only had one choice there. But suppose that we are deriving something, here's a variable, and stuff can appear before or after it. So let's just say that we're going to apply a rule of the form A goes to X. X may be a terminal, a variable, or a combination, whatever. It's just a rule. Well, if we apply that on that variable right there, what will the result be? So what were we always doing? We took a variable that we wanted to replace and replaced it with the right-hand side of the rule. If we're going to apply this rule, what will this derivation look like after we apply it?
Just replace A with X.
Right. So everything before is exactly the same. So nothing here changes, but the A now turns into an X, and everything after stays exactly the same. Okay? So the placement of this variable A doesn't matter. It doesn't matter if it's at the beginning, the middle, or the end, or wherever. It doesn't matter what's on either side of the A. So, in fact, this rule application is independent of the context in which the variable appears. It doesn't matter what's right around the variable or anywhere else. The only thing that matters is the variable. So that's what we're going to take a look at now. So a context-free grammar, and we're lovingly going to call it CFG, is a grammar where all rules are of the form A goes to X, where A is a variable and X is a combination of variables and terminals in any order, any number of them. And I can explain that notation in a second. But the idea behind this is always one variable on the left side and anything you want on the right side, as long as it's a finite string of variables or terminals in any order, but you can have anything you want on the right side. Okay? So by this notation, I mean, so we all know what star means, right? So that means just pick something from the set in which it's starring some number of times. Well, the set that we're considering is just variables and putting the terminals into one gigantic set and just picking from that set over and over. Okay, so that's just any number of variables and terminals. Okay, any questions about that? Okay, well, let's see. Was this a question I asked? Yeah, I was going to do a little exercise, but it's on your quiz, so I'm not going to do that.
If you only have variables on the right side, if you don't have
So would that be if it was only in one rule, or is it with every rule? With every rule? Okay. So if we have, like, say, A goes to B, C goes to B goes to A, C, A, or something. So well, let's see. So let's actually try to figure this out. So can I make a string full of terminals with this grammar? No. And in fact, we can even expand upon that. It doesn't have to be just variables. What if every rule has a variable on the right side, regardless of the number of terminals? So suppose I took this grammar and I added all of these terminals to it. Then every single rule still has a variable, and so I can never remove the variable. You can actually expand this further. You could, in fact, have some some rules where it's only terminals on the right side, and still have them be unreachable, or at least, even if they're reachable, you can still make a grammar such that there's no way to derive a string of terminals. In fact, way later in the semester, we're going to be talking about algorithmic problems related to DFAs, NFAs, context-free grammars. And one of the interesting problems we'll look at there is testing whether a grammar's language is empty. So whether it can generate a string at all. So it turns out to be a really interesting question, and we'll address it there. But yeah, the language of this grammar is empty. Any questions about that? So one of the really important things about context-free grammars is that they run basically every compiler you've ever used. So if you use a C compiler, a Java compiler, a Fortran compiler, a Python parser, every single one of those has, maybe not exactly, but close to a context-free grammar inside of it somewhere. And let's try to address why that is. So how many of you have ever had this experience where, let's just say you're compiling a Java program or something, and you compile it, it says, oh, there's an error right here, and it says that we looked for a missing curly brace but couldn't find it. And then when you fix it by putting the extra curly brace in there, now you have 100 errors. How many of you have ever had a similar type of experience? Ever wonder why that is? So here's what happens. So your compiler is parsing whether or not the curly braces, the parentheses, and all of that are what are called balanced, and see whether or not they're balanced first. And if it is balanced, then it actually parses the real stuff, the real code. So the parsing of actually both of those, but primarily the parsing of whether the parts are balanced of curly braces and parentheses, that's done with a context-free grammar. And we can actually see how to do that by looking at this example. So let's see. So let's look at the language L, which is the set of all, let's just do parentheses to make it easy to see. So I'm going to have W be an element of parenthesis, parenthesis, I'm making it a different color so that it's easier to see, where W is balanced. And by balanced, I mean we can't have something like 2 left parentheses and then a right parenthesis. And we can't have something like that. We can't have something like left and then right. Right then left. So this wouldn't be balanced. So another way to phrase it is, it has to start with the left parenthesis, and there is a matching right parenthesis somewhere. So yeah, we can't have that. So one way to actually phrase it is we have a left parenthesis and somewhere else we have a right parenthesis somewhere. What has to happen in the middle? If this thing is balanced, yeah.
The exact same thing must happen over and over.
Yeah, so the stuff in the middle must also be balanced. But if we just carry out like this, then what happens is you'll have a left here and a right here, and then you expand in the middle part. That part has to be balanced, 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 balanced. And then basically what we'll have is 0 to the n, 1 to the n, the same structure. Because if we just leave it like this, then that means that we'll have only lefts at the beginning and only rights at the end, and then they meet in the middle. But that's exactly the 0 to the n, 1 to the n language, just different characters. So what we have to allow is, well, stuff can appear before this left parenthesis, right? And stuff can appear after the right parenthesis too. And what do we know for the part before the left and the part after the right? What do we know about those two areas?
They should balance each other.
They should also be balanced. Because if you have balanced in the middle, well, anything that appears after or before, that part must also be balanced in some way. So, in fact, this is balanced too, that's balanced too. Any questions about that? Or it could be the empty string, of course, but. So let's actually make a grammar for this. So what we can do and how you should approach these problems too is assume that the start variable does the right thing in some kind of inductive type reasoning. So we assume that, say, the start variable s can make a balanced set of parentheses. Then, from that, how can we incorporate this into a rule? So let's actually do it. Well, we know that s goes to empty must be a rule because the empty string is balanced. Every left matches with a right exactly, and between and outside, they're also balanced. Well, the other thing that can happen is we have this situation where we have a left stuff and right and stuff on either before or after. So how can we make a rule for this? Again, assume s does the right thing.
Would be S left parenthesis, S right parenthesis, S.
Exactly. Cool. So there's a great phrase for this. By assuming that the variable does the right thing, a professor in the University of Illinois has come up with this phrase of, we're calling the recursion fairy. So we're calling recursion here and just saying, sprinkle some magic dust and say, oh, this variable must be right. So we're assuming that the s variable does make balanced strings. And going off of that assumption, if we have a left and a right here, well, a balanced string must appear before, a balanced string must appear in the middle, a balanced string must appear on the right. And that's exactly what the grammar says. So let's actually generate a string. So let's say we want to try to generate, let's make it non-trivial. So left, left, right, right, left, right. And so let's say I want to actually generate that string. So in any derivation, a set of rule applications, where do we have to start? Start variable. So we have to start with the start variable, and then we got to apply a rule. So which one of those two rules should we apply? Yeah, I hope some of the rest of you participate too. So it's not just Ethan. So let's apply a rule. The second one, if we apply the first one, we're dead in the water. So we better apply the second one. So S So now let's apply another rule. So yeah, go ahead. You don't actually. It's we'll see a reason later that you don't actually need this. So there's a simpler grammar, but this just covers all the bases that we need. Because we know that if you have a matching pair, then must be balanced on all three places. But it turns out you can assume that one of them is not there, and there's a reason why we would want to consider that option and not this one. So, in fact, we're going to address it right now. So, before with regular grammars, we only had one choice of a variable to pick to apply a rule with. How many choices do we have here? How many S's are on the right side? 3. So which one do you want to work with?
I'd say first we use the middle one.
The middle one? Okay, cool. So remember, it's a context-free grammar. Not paid, free. So that means that everything else in the string stays put, doesn't change. So I'm going to copy this down, move these two over here so we can make some room. And so now we want to expand the middle S with a rule application. So which rule do you want to use? So let's use the second one. So as was suggested, so let's apply the second rule. So that says we're going to basically make a whole copy like this, paste it in there. Ooh, that looks trippy. Okay, so we applied a rule. Now what?
We could work with the private match strings go all the way to the one on the right.
Okay, so the first 4 S's, what do you think we should do with those? Yeah, apply the other rule, yeah. So here I'm going to work with one variable at a time. Notice something interesting. Does it matter which S I work with? Doesn't matter. We'll address that point later. So I apply a rule, then I apply another rule, make this S go away. Apply another rule. The middle S goes away. And then one more rule. It's a little tedious, but it's good to do this at least once to see how things work. So we just eliminate one of the, not eliminate, I apply a rule that makes the S go away. So it's not like you can just strike out one of the variables you don't like. You have to apply a rule, and we are. but it makes the variable go away. Okay, so then we've still got a variable in there, so what are we going to do with it?
Apply the second rule again.
Yeah, apply the second one. So then we'll have, let's see. So this S goes away. I'm going to copy what we did before and paste it down here. Oh, jeez. A lot of rules here. So can you tell me what the last three S's are going to do? Yeah, we're going to apply the first rule. So for the interest of time and our sanity, I'm going to say that we're just going to apply S goes to empty 3 times in here, and then eventually we'll arrive at the string that we want. And then now we got a string full of terminals. Good. Cool. Any questions about that? Yeah.
Sorry, I'm just looking at why we had to start with S, parentheses, S, parentheses.
Yeah, because if I just applied S, the one variable S that I have, I start with a single variable and nothing else. Well, then if I replace it with the empty string, there's no variables anymore. And so I can't replace it with anything to obtain this string. I can apply that to get the empty string if I wanted to. So it's just a set of rules to generate strings. But if I'm after this particular string, I better apply the other rule.
So, sorry, can I just ask a weird follow-up? So if
Yeah.
you have like, maybe like a third pair of parentheses in that like first and second parentheses. So if it was like,
Oh, yeah, like this?
yeah, so then would we need 5 S's?
Yeah, you would need to expand that more. Yeah. So like in the second line, the innermost S, you would need to apply the second rule yet again.
Or, yeah.
There's no way this is like how it works in real life, is it?
No,
I was like,
thankfully. And we'll actually, I'm not sure how much time we'll have to do that, but I can actually talk about at some point the real algorithm that really is used in figuring out whether a string can be generated at all. And it actually relates to something that we're going to talk about later this week, something called Chomsky normal form.
Does the context-free grammar always have a start variable?
Yeah, so all grammars have a start variable, so you always start there. Other questions? So let's look at this again. So if we look at, say, this at this point right here, so we just applied one rule and that's it. And what we did was we looked at the innermost S and applied a rule to it, and then we got the doubly nested set of parentheses, and then we dealt with it accordingly. Could we interpret or do this in another way so that these two parentheses right here are the last two, not the ones corresponding to the innermost two? Yeah. So what I mean is, in our derivation, what we did was this first rule corresponds to that parenthesis and that one. That's what we actually did. Could we redo this so that the same rule, these two parentheses are these two instead? Yeah. So that's actually two different ways of generating the exact same string in this grammar. That's kind of annoying, isn't it? So if you are implementing this for a compiler, what would you rather have? Would you rather have a single way of generating a string or to have multiple ways of generating a string? Which one seems better for debugging? One, I think, seems better because if something goes wrong, you know exactly how the grammar was derived or the string was derived. Here, if there are multiple ways, we have no information about what can happen. In fact, you can design a grammar so that you can have a string have infinitely many ways of being generated. Let me show you. So if you have, say, S goes to empty or S, then how many ways are there to generate the empty string? Infinitely many. Because I can just apply S goes to S as many times as I want, over and over and over, and then eventually generate the empty string. So that's kind of annoying that a grammar's like this. So when this happens, we call the grammar ambiguous. So a grammar, I'm not going to finish the definition here because there's one more thing I need to discuss, is ambiguous if there exists a string that has at least two different, and I'm going to leave a space here for a word that I'm going to put there, derivations. Okay? So what do we mean by different? So let's look at this example to motivate it. So suppose I have this grammar. S goes to A, B, where A and B are variables. A makes a single character A, B makes the single character B, and that's it. So a pretty simple grammar, so nothing really complicated. The only string I can make with this thing is AB, a lowercase ab. Well, I look at this and I say, well, if I want to make the string AB, what could we do? I'm going to draw a line here. So if I wanted to make the string AB from the start variable S, what do I have to do? Or what could I do? Which rule do I have to apply first?
You have to go to A and B.
I have to go to AB, capital AB. Now what?
A would go to B.
Yeah, so I can make the capital A, apply a rule to it, and make the lowercase a if I wanted to. And then I can convert the capital B into a lower b, and then I have a string, AB. But suppose I did it this way. If I did the first rule, I have no choice there, but I did the variable B go to B first. So I apply the rules in a different order. And then I apply A goes to lowercase a. So are these really different? Technically, yes. But are they applying the same rules, essentially, in the same way? So like, when I generate this lowercase a right here, in both places, that came from the same rule. So if I have a bunch of variables on the right side, because this is a context-free grammar, it doesn't matter what order I apply the rules in. So what we need is, what if, because it's a context-free grammar, it doesn't matter which order I process the variables in. So what we are going to look at are what are called leftmost derivations. So what does a leftmost derivation mean? That means we apply a rule to leftmost variable first. So if we look at the little grammar we made down here, well, leftmost derivation means we have to process the capital A first and then process the capital B. And so since there's only one variable and one rule to apply, there's no way to make the string in two different ways. Whereas the one before, what we could do is the left and the right parenthesis could be interpreted as the last one or the first set of parentheses. So it's not really clear which one it actually corresponds to. So in fact, the string that we just made here actually has two different leftmost derivations because we can interpret the parentheses in two different ways. They could have come from two different sets of rules. Isn't that pretty cool? So this grammar, not this little one, this grammar for balanced parentheses is ambiguous. So the goal then, of course, for anyone implementing a compiler is to what? Do we want an ambiguous grammar or an unambiguous grammar? Unambiguous sounds better to me. So what you may think is, well, say for any context-free grammar G, is there an equivalent unambiguous CFG, context-free grammar? So if I have a grammar which may or may not be ambiguous, is there an equivalent one that has no ambiguity? So it's basically related to the question of like NFA to DFA. If I have this NFA which allows to have choices, could I make a DFA that has no choice? That might be something you want to consider. And so what do you think? Is this true or not? Just based off your limited exposure to this. Yes? Anyone say no? Believe it or not, the answer is no. So, no, there exist languages for which every CFG for them is ambiguous. So one thing before we break for today. So here's something that students mess up a lot, so I hope you don't. It's not right to say that the language is ambiguous. It's right to say that the grammar is ambiguous. The language may or may not have an unambiguous grammar. So just because there exists an ambiguous grammar for a language doesn't preclude there existing an unambiguous grammar for the same language. It may or may not exist, but it's just that if an ambiguous one exists, doesn't mean that there doesn't exist an unambiguous one. So I'll see you on